In the chilling grip of the Cold War, as the geopolitical landscape solidified into an iron curtain stretching across continents, the U.S. Army faced a unique and daunting logistical challenge: how to move massive amounts of cargo across the vast, roadless, and utterly hostile terrains of the Arctic. Standard trucks and even tracked vehicles proved inadequate against the crushing snows, treacherous ice, and unforgiving permafrost. It was in this crucible of necessity that the most ambitious ground vehicle in history was conceived: the LeTourneau TC-497 Overland Train. This was not merely a truck. It was a land leviathan, a multi-sectioned metal snake stretching over 170 meters, 550 feet long, designed to conquer environments where no conventional transport could survive. Conceived by the visionary LeTourneau, a titan of heavy machinery, the TC-497 was an engineering marvel that looked like something ripped from the pages of a science fiction novel. It was a self-propelled convoy of connected modules, riding on 54 colossal 4-meter, 10-foot diameter wheels, each powered independently by a revolutionary electric drive system. The Overland Train was a $25 million attempt to defy nature itself, promising to transport hundreds of tons of military supplies and personnel across thousands of kilometers of frozen wilderness, reaching speeds of up to 30 kilometers per hour. However, this walking fortress of steel and rubber, built for a future of extreme exploration, ultimately succumbed to the very environments it was designed to dominate. Its sheer scale, its immense complexity, and the brutal reality of operating in the world's most desolate regions proved to be its ultimate undoing. Before we delve into the thunderous roar of its 10 gas turbine engines and the terrifying physics of its independently powered wheels, please take a moment to hit the like button and subscribe to Never Built. We're the chroniclers of the lost futures, uncovering the massive engineering projects that were too ambitious for their own era. We promise you this: stay with us until the final segment of this series, and you will learn about the permafrost shear phenomenon, the specific geological interaction that caused the Overland Train's immense weight to literally turn the frozen ground beneath it into an impassable, bottomless slurry, effectively burying the world's largest land vehicle in its own path. The genesis of the Overland Train concept was rooted in the extreme logistical demands of establishing radar stations and military outposts in the remote Arctic regions during the early stages of the Cold War. Conventional supply lines, relying on sporadic airlifts or seasonal sea voyages, were both unreliable and prohibitively expensive. The U.S. Army needed a robust, all-weather, all-terrain solution. LeTourneau, already famous for his massive earth-moving equipment, offered a radical solution based on his patented electric drive system. Instead of a single central engine driving all wheels through complex mechanical linkages, the TC-497 utilized a series of independent power cars and cargo modules, each equipped with its own electric motor integrated directly into the hub of every wheel. This meant that each of the 54 wheels acted as its own miniature locomotive, providing unparalleled traction and flexibility. If one wheel lost grip, the others would compensate, ensuring continuous forward motion over uneven terrain. The front command car alone was a behemoth, a fully articulated, self-contained unit resembling a small submarine, housing the driver's cockpit, communication equipment, and a powerful gas turbine engine. The subsequent modules, each equally massive, could be added or removed depending on the mission profile, allowing for a payload capacity that dwarfed any truck convoy imaginable. The propulsion system and its electrical network were an engineering marvel of distributed power. The TC-497 was driven by no fewer than 10 1,170 horsepower Solar Saturn gas turbine engines, generating a total of 11,700 horsepower. These turbines powered massive generators, which in turn supplied electricity to the electric motors within each wheel hub. The entire system was a colossal, self-contained rolling power station, capable of navigating extreme temperatures and altitudes. However, this distributed power also introduced an unprecedented level of complexity. The electrical cabling running between the 12 individual sections of the train stretched for hundreds of meters, vulnerable to the brutal cold, ice, and constant flexing of the articulated joints. A single short circuit in the Arctic wilderness could disable an entire section, leaving hundreds of tons of cargo stranded. This was the ultimate challenge of electromechanical reliability. Attempting to maintain a perfectly insulated and operational high-voltage network in an environment designed to degrade every single component. Furthermore, the crew environment and self-sufficiency were designed for extended missions in complete isolation. The front command car was essentially a mobile base camp, complete with sleeping quarters, a galley, a lavatory, and even a small workshop for emergency repairs. The 4 to 6 crew members could operate the overland train for weeks without external support, relying on onboard fuel tanks that held tens of thousands of gallons of diesel. The sheer scale of the vehicle meant that routine maintenance was a monumental task. Changing a single 4-meter wheel required specialized onboard jacking systems and hours of strenuous labor in sub-zero temperatures. The concept was one of total autonomy. But this self-reliance came at the cost of immense complexity. The psychological toll of operating such a colossal, slow-moving machine in the relentless silence of the Arctic, knowing that rescue was days or even weeks away, created an environment that pushed human endurance to its limits. The articulation and maneuverability of the TC-497 were revolutionary, designed to allow the multi-section train to navigate tight turns and uneven terrain despite its immense length. Each module was connected by a hydraulically articulated joint that allowed for both vertical and horizontal movement, mimicking the flexibility of a gigantic snake. The operator in the command car steered the entire train using a joystick, sending electrical signals to independently control the steering of each individual wheel. This electronic brain system was cutting edge for the 1950s, a precursor to modern drive-by-wire technology. However, the sheer physical inertia of 450 tons of steel and cargo meant that precise control was often an illusion. A slight delay in operator input could send the massive train veering off course, or worse, cause the entire articulated structure to jackknife in deep snow, leaving it helplessly stuck. Project LeTourneau was a triumph of distributed control, but it was fighting against the immutable laws of mass and momentum in the most unforgiving landscape on Earth. The deeper we investigate the mechanical heart of the LeTourneau TC-497, the more we uncover the ice trap of the 4-meter wheels. While R.G. LeTourneau believed that sheer size would conquer any obstacle, the physics of ground pressure in the Arctic proved to be far more treacherous. These massive 54 wheels were not just made of rubber. They were complex industrial components, each with its own internal electric motor and planetary gear reduction system. The theory was that a larger surface area would allow the 450-ton train to float over the snow. However, in practice, the massive heat generated by the electric motors inside the hubs created a thermal sinking effect. In sub-zero temperatures, the heat from the motors would slightly melt the top layer of ice, or permafrost, which would then immediately refreeze around the tires when the train stopped for even a few minutes. The world's largest land vehicle wasn't just getting stuck, it was literally being frozen into the Earth's crust, requiring the crew to use thermal torches just to break the wheels free from the Arctic's icy grip. The fuel logistics of the gas turbine engines represented a secondary engineering crisis. To power the 10 solar Saturn turbines, the overland train had to carry an ocean of fuel. The TC-497 consumed thousands of gallons of diesel every few hours of operation. To manage this, several of the trailing modules were nothing more than massive heated fuel tanks. However, at temperatures of -40 or 50 degrees Celsius, diesel begins to reach its cloud point, where paraffin wax starts to solidify, clogging filters and stalling engines. This meant that a significant portion of the train's generated electricity had to be diverted back into heating the fuel lines and tanks just to keep the cold monster alive. It was a thermodynamic parasite, a machine that consumed its own energy reserves at an alarming rate just to prevent its own internal systems from freezing solid. The logistics of supplying such a fuel-hungry beast in the middle of a roadless wilderness meant that for every overland train deployed, a secondary fleet of smaller vehicles would likely be needed just to keep its tanks full. Furthermore, the electromagnetic interference, EMI, of the massive cable network created a localized chaos that the 1950s technology struggled to contain. The high-voltage lines running the length of the 170-meter train generated immense electromagnetic fields. In the Arctic, where the Earth's magnetic field is already volatile and the aurora borealis creates natural atmospheric interference, the overland train's own electrical noise often blinded its internal electronic brain. The signals from the command car's joystick would become corrupted by the time they reached the 12th module, causing the rear wheels to steer in the wrong direction or fail to provide power at critical moments. This led to the whiplash effect, where the tail of the land train would begin to oscillate uncontrollably, threatening to overturn the cargo modules and snap the articulated joints like brittle twigs. The TC-497 was essentially fighting a constant internal war between its high-tech electrical nervous system and the raw, unshielded reality of the polar environment. The internal maintenance hell of the command car's engine room was a vision of claustrophobic engineering. Because the command car had to be pressurized and insulated against the Arctic gales, the 170 horsepower turbine was packed into a space so tight that mechanics had to perform repairs in specialized, slim-profile thermal suits. The noise inside the cab, despite the heavy, lead-lined insulation, was a constant, high-pitched turbine scream that vibrated through the teeth and bones of the crew. Communication was only possible via specialized headsets, and even then, the constant vibration made reading delicate instruments nearly impossible. The overland train was a machine of mechanical brutalism. It was powerful, yes, but it demanded a level of human sacrifice and physical endurance that few crews could maintain for the weeks required for a trans-Arctic journey. Every hour of movement required 3 hours of intensive maintenance, turning the journey into a slow, grinding battle against mechanical entropy. Moreover, the tidal force of 450 tons on permafrost revealed a geological flaw that LeTourneau had underestimated. When the train moved over seemingly solid frozen ground, its immense weight created a pressure wave in the soil. This led to the ground liquefaction paradox. The pressure of the 54 wheels would briefly turn the frozen moisture in the soil into liquid, creating a temporary layer of slick mud beneath the snow. As the train moved slowly, it was effectively sliding on its own path, losing traction and causing the articulated modules to drift sideways. The king of the Arctic was being defeated by the very ground it was built to conquer, proving that no matter how many wheels you added, the fundamental physics of mass and gravity would always find a way to trap the giants. The downfall of the LeTourneau TC-497 Overland Train was not just a failure of rubber and steel, but a victim of the vertical logistics revolution that changed the face of the Cold War. As the Overland Train was undergoing its grueling tests at the Yuma Proving Ground, a new titan was rising in the sky, the heavy lift helicopter. The U.S. Army realized that while the TC-497 was a mechanical masterpiece, it was fundamentally tied to the ground, a ground that, in the Arctic, was constantly shifting, freezing, and swallowing everything in its path. A fleet of Sikorsky CH-54 Tar-Hay sky cranes could transport the same amount of cargo in hours that the overland train would take weeks to deliver. This was the aviation death knell for the land train. Why spend millions maintaining a 170-meter mechanical snake that could be stopped by a single crevasse or a sudden blizzard when you could simply fly over the obstacle? The TC-497 was an 18th-century logistics dream built with 20th-century technology, and it was being made obsolete by the very progress it tried to represent. The catastrophic maintenance debt of the project became an insurmountable wall for the military budget. By the time the train reached its full configuration of 12 modules, the mean time between failure, MTBF for its critical systems, had dropped to an unacceptable level. With 54 independent electric wheel motors, 10 gas turbines, and miles of high-voltage cabling, something was always breaking. In the Arctic, a minor repair like replacing a faulty electric motor in a wheel hub became a life-threatening operation. The crew had to work in specialized heated tents erected around the wheel, fighting the wind and the cold, while the rest of the 450-ton train sat idle, consuming precious fuel just to keep its systems from freezing solid. This created a maintenance fuel spiral. The longer the train sat still for repairs, the more fuel it consumed for heating, which in turn required more cargo modules to be dedicated to fuel, leaving less room for the actual supplies it was meant to carry. The cold monster was eating its own purpose, becoming a logistical burden rather than a solution. Furthermore, the shattering of the indestructible image occurred during the deep snow testing phases. LeTourneau had promised that the 4-meter tires would ride over the snow, but the reality was the compaction crisis. As the first few modules passed over a patch of snow, they would compact it into a dense, icy track. However, the subsequent modules, weighing hundreds of tons, would then apply enough pressure to shatter this newly formed ice crust. The middle and rear sections of the train would suddenly drop into the soft snow beneath, a phenomenon known as post-compaction sinking. This meant that the train was constantly fighting against its own tracks. The front command car would move smoothly while the tail of the train was dragging through a chaotic slurry of broken ice and deep powder. This placed immense stress on the hydraulic articulation joints, which began to leak and fail under the non-stop twisting and pulling forces. The land leviathan was literally being torn apart by the very path it was creating. The economic hubris of Project LeTourneau was also laid bare when the final cost per ton mile was calculated. It was discovered that operating the overland train was nearly 10 times more expensive than using conventional ice-strengthened ships or specialized track tractors. The TC-497 required a moving army of support staff, specialized refueling stations, and an incredible amount of spare parts. It was a white elephant of the permafrost, a machine so specialized that it couldn't be used anywhere else, yet so expensive that it couldn't be justified for its intended role. The U.S. Army, facing the escalating costs of the Vietnam War and the development of nuclear ICBMs, decided that the era of the land train was over. The project was suffering from strategic irrelevance. In a world of supersonic jets and satellite tracking, a 170-meter steel snake moving at 20 kilometers per hour across the ice was a relic of a slower, more industrial age. Moreover, the nuclear winter of the atomic icebreaker competition added a layer of geopolitical pressure. While the U.S. was building land trains, the Soviet Union was successfully deploying nuclear-powered icebreakers like the Lenin, which could clear paths for entire fleets of conventional ships. The American military realized that dominating the Arctic required a maritime strategy, not a terrestrial one. The overland train was a landlocked titan in a war that was increasingly focused on the oceans and the upper atmosphere. The project was officially mothballed in the early 1960s, with the massive command car eventually ending up as a rusting curiosity in an Alaskan museum, while the cargo modules were sold for scrap. The Arctic King had been dethroned not by an enemy army, but by the cold, hard logic of the cost-benefit ratio. It was a machine that proved we could build giants, but it also proved that the Earth has a way of making those giants feel very, very small. The physical death of the LeTourneau TC-497 Overland Train did not mean the total extinction of its radical engineering DNA. Instead, the project underwent a mechanical metamorphosis. While the U.S. Army abandoned the idea of a 170-meter land snake, the individual technologies that made it possible, most notably the high-torque electric wheel motor, became the cornerstone of the modern heavy-duty mining industry. Today's gargantuan ultra-class haul trucks, like the Belaz 75710 or the Liebherr T282B, are the direct descendants of the TC-497. They use the same principle of a diesel-electric drive system where a central engine acts only as a generator for electric motors located in the wheels. R.G. LeTourneau's Arctic Monster proved that electricity, not mechanical gears, was the only way to move hundreds of tons across uneven surfaces. The project was a functional martyr. It failed as a military transport, but it succeeded as a laboratory for the future of planetary-scale earth-moving. The archaeology of the Desert Ghost provides a haunting visual epilogue to this story. While most of the cargo modules were unceremoniously cut into scrap metal in the 1960s, the massive command car of the TC-497 refused to die. For decades, it sat abandoned at the Yuma Proving Ground in Arizona, a gargantuan white hull bleached by the sun, looking like a stranded spaceship from a forgotten civilization. It was a monument to the era of absolute scale, a time when engineers believed that any problem of nature could be solved with more horsepower and more rubber. In recent years, this command car was moved to the Heritage Center at Yuma, where it stands as a silent sentinel. To look at it is to understand the technological hubris of the Cold War. A machine built to conquer the North Pole, now standing in the middle of a burning desert, its 4-meter tires still holding the ghost of an ambition that the world simply couldn't afford to sustain. The psychological legacy of the land leviathan continues to resonate in our cultural obsession with giant machines. The Overland Train was the physical manifestation of the frontier spirit translated into industrial terms. It represented a belief that humanity was no longer limited by geography, that we could build a moving city that could ignore roads and create its own path. But the failure of the TC-497 taught us a bitter lesson about environmental friction. No matter how many wheels you add or how many thousands of horsepower you generate, the Earth's climate and geology, the mud, the ice, and the shifting permafrost remain the ultimate gatekeepers. The Overland Train was the last of the analog giants before the world shifted toward the digital, the compact, and the aerial. It was a 450-ton proof that sometimes the most advanced solution is not the one that fights the environment, but the one that learns to fly above it. Today, as we look toward the colonization of Mars or the construction of lunar bases, the blueprints of Project LeTourneau are being dusted off once again. The concept of a modular electric convoy is perfectly suited for the roadless, cratered surfaces of other worlds where helicopters cannot fly and infrastructure does not exist. The Overland Train was not a mistake. It was merely born on the wrong planet. It was a machine designed for a world with more space and fewer limits. A space-age nomad trapped in a Cold War reality. Its history is a reminder that the path to the future is often paved with the rusted remains of the giants that tried to get there first. The final question for you is this: as we face new challenges in the most remote corners of our planet, will the land train make a comeback as an eco-friendly electric alternative to ships and planes? Do you believe R.G. LeTourneau was a madman who ignored the laws of physics, or a misunderstood genius whose ideas were simply too big for the 20th century? Let us know your thoughts in the comments and tell us. If you had the chance to spend a month living and working inside this 170-meter cold monster, would you take the risk? Or is the Arctic no place for a machine of this size? If you found this deep dive into the 170-meter Arctic Leviathan and the most ambitious land vehicle failure in history fascinating, like this video and subscribe to the channel. We are uncovering the massive engineering and the lost futures of the projects that were never built.